coupled circuits. Here the mutual inductance concept is present. Mutual inductance concept is present when the magnetic circuit is having the more than one inductor. The magnetic circuit is having more than one inductor. In this example, to explain this mutual inductance concept, I have taken simple example as a transformer. Correspond this transformer here, this N1 is the number of turns in the primary winding. This N2 is the number of turns in the secondary winding. Now correspond case 1, the source is connected to only primary side. Correspond case 1, the source connected to only primary side, and secondary is the open circuited. In this example, whenever the V1 source is connected, it circulated current of I1. Now this I1 current produces the flux of the pi1. This pi1 we can divide this into two components. One is the pi11, other one is the pi12. Now corresponds example here, the flux which are circulating around its own inductor. Is a pi11. Here the name of this pi11 is a leakage flux. Now other one is a pi12. The flux which are circulating around the first inductor as well as second inductor. Is the mutual flux. The flux which are circulating around the first inductor and the second inductor is the mutual flux. Or one more name for this one is the useful flux. Mutual flux or the useful flux. The flux which are circulating around the first one as well as second inductor, we can call it mutual flux or the useful flux. Then if you come to first inductor here, pi11 is linking and pi12 also linking. Correspond to this first inductor here, pi11 is linking and pi12 also linking. And sum of these two fluxes equal to pi1. Now with respect to Faraday's law, induced EMF is directly proportional to rate of change of flux. Now based on proportionality, here I am trying to introduce one constant. That constant is the N1. In this example, this N1 indicates the number of turns in the first inductor. Here the N1 indicates the number of turns in the first inductor. Now same expression we can write this as Can we write this? If these two terms are cancelled, this expression obtained. Now for this inductance, previously we already discussed the basic formula. For the basic formula for the inductance, L equal to N pi by I. Here the N1 pi1 I1. This entire term replaces by inductance. Corresponds example, this entire term replaces by inductance. L1 dI1 by dt. In this example, EMF induced in the first inductor. EMF induced in the first inductor is due to its own flux. The pi1 produces which one here? Current of the first inductor only. EMF induced in the first inductor is due to its own flux. own flux. Thereby here in this example, this E1 is named as a self-induced EMF. In this example, this E1 named as a self-induced EMF. Self-induced EMF. Come to the second term. Correspond second term. Come to the second inductor. Now correspond second inductor, if you verify which flux are linking here. Correspond to this second inductor, which flux are linking here? Pi 1 2. This pi 1 2 flux is linking the second inductor. Thereby correspond second inductor we can conclude as a this E2 directly proportional to d by 2 by dt. d by 2 by dt. Now based on the proportionality, here I am trying to introduce one constant. That constant is the N2. That constant is the N2. Now from this one we can write this as this E2 equal to N2 now we can write this. In this example here, if these two terms are cancelled, same expression obtained. Here one more new term is introduced, M21. N2 pi 1 2 by I1. Now if you observe carefully here, N2 is the number of turns second inductor. N2 is the number of turns second inductor. Now this pi 1 2 is the mutual flux of the first inductor. I1 is also correspond to first inductor. I1 also correspond to first inductor. Then here in this example, this entire term corresponds example here. This entire term replaced by M1. This E2 equal to, we can write this as a M21 dA1 by dt. In this one here, EMF induces second inductor. Corresponds example, EMF induces second inductor is due to current of the first one. Thereby here, this E2 is named as a mutual induced EMF. This E2 is named as a mutual induced EMF. The meaning of M21 is a mutual inductor second inductor with respect to first one. Okay. Don't get confusion. This pi 1 2 and M21. Pi 1 2 is a mutual flux. Pi 1 2 mutual flux. But M21 meaning is a mutual inductor second inductor with respect to first one. Now write all these steps. Copy कर लीजिए. Write all the steps. Dear students, for electrical students, again separately they won't mention a magnetic coupled circuit, because magnetic coupled circuit is a part of the electrical engineering only. Based on this one, you do entire analysis in electrical machines. That's why don't think as a magnetic coupled circuit is not mentioned in the gate as a kuch bhi nahi hai. Is the required. In electrical machines, many cases, everywhere use the word as a mutual inductance and inductance concept. Without inductance concept, there is no AC machines, no AC generator and no AC motor also. Okay? And with respect to competitive exams and gate point of view, ESC point of view, magnetic coupled circuit is important. For electronic circuits, for electrical, not for electronic students, for them it is not very important, but for electrical important. Okay? Come to case 2. Now correspond case 2 here. Correspond case 2, the source is connected to only secondary side. Correspond case 2, source connected to the only secondary side and primary is the open circuited. And this primary is the open circuited. In this example, this V2 V2 produce the current of the I2. This I2 produce the flux of the pi2. Can you repeat the same steps again? We can separate as the two parts, pi2 2. It is the pi2. Pi2 2 and pi2 1. Corresponds example, the flux which are circulating around its own inductor is called as the leakage flux. And the flux which are circulating around the first one and as well as second one. The flux which are circulating around the first one and as well as second one, we can use word as a mutual flux. Mutual flux. Another one more name for this is the useful flux. One more name is the useful flux. The flux which are circulating around its own inductor is called as a leakage flux. For this one, give the name as a pi2. And the flux which are circulating around the first one and as well as second one. The flux which are circulating around the first one and as well as second one is called as a mutual flux. It is the mutual flux. Then correspond to the second inductor, pi2 is linking and pi2 also linking. Pi2 is linking and pi2 also linking. Now sum of these two flux equal pi2. Now with respect to this Faraday's law, here, induced EMF is directly proportional to rate of change of flux. Corresponds second inductor, pi2 is linking and pi2 also linking. Now based on proportionality, here I am trying to introduce one constant. That constant is the N2. In this example, if these two terms are cancelled out, again the same expression obtained. What is the basic formula for the inductance? L equal to N pi by I. Basic formula for inductance is L equal to N pi by I. Now in this example, this entire term is replaced by L2. Now observe. Now EMF into second inductor is due to its own current. Thereby here this E2 is named as a self-induced EMF. Now similarly correspond first inductor. Now correspond to this first inductor, only which flux are linking here? Pi2 1. Corresponds first inductor, only pi2 1 flux is linking. Again with respect to this Faraday's law, induced voltage in the first inductor is directly proportional to. Now based on the proportionality, here I am trying to introduce one constant. That constant is the N1. N1. Corresponds example, if these two terms are cancelled out, again the same expression obtained. One more new term is introduced. M12. Now observe. Now corresponds example, this meaning of M12 is a mutual inductance of the first inductor. M12 meaning is a mutual inductor of first inductor with respect to second one. Now here this entire term corresponds example, this entire term replaced by M12. Mutual induct in the first inductor with respect to second one. With respect to second one. In this example here, induced EMF in the first inductor is due to current of the second inductor. Induced EMF first inductor is due to current of the second one. Thereby here this E1 is named as a mutual induced EMF. E1 is named as a mutual induced EMF. Mutual induced EMF. Okay. At all the steps. To observe carefully. For this particular example, if you observe carefully, in the case 2, the source is connected to only second inductor. The source connected to only second inductor, and first one is the open circuit. Source connected to only second inductor. When the source is connected to only second inductor at that instant, the sign of the self-induced voltage, and mutual induced voltage both are the same. At that instant, the sign of the self-induced voltage and mutual induced voltage both are the same. Sign of the self and mutual induced voltage both are the same. On the other hand, if you connect any other inductor here, if you connect the load here in this inductor, now corresponds example, if you connect any load here, now current is present in the first one and as well as the second one. Current is present in the first one and as well as second inductor. When the current is present in the first one and as well as second inductor, at that instant, the sign for mutual induced voltage, it may be either positive or the negative. At that instant, the sign of the mutual induced voltage, it may be either positive or the negative. That means two possibilities are present. Then let us check it out when this positive negative signs are present. So now check करेंगे when this positive and negative signs are present. Now for the verification of this one, let us take one simple example. For the verification of this one, let us take this simple example. Now corresponds example with respect to front view. All these arrow mark directions, 4-finger direction both are the same. In this example, with respect to front view, all these arrow mark direction, 4-finger direction both are the same. But the 4 fingers indicate the direction of current. This thumb indicates the direction of flux. Now correspond this particular example with respect to front view, all these arrow marks indicate the direction of current. Thumb indicates the direction of flux. Then what is the direction of flux for this one? Downwards or upwards? Upwards. Corresponds example, what is the direction of flux for this one is upwards. Pi1. Come to second inductor. Again corresponds second inductor with respect to front view. All this arrow mark direction, 4-finger direction both are the same. With respect to front view, all this arrow mark direction, 4-finger direction both are the same. Then what is the thumb indicate the direction of flux? But direction of flux downwards or upwards? Upwards. In the magnetic circuit, every flux line form a closed path. In this particular example, this pi1 completes the closed path in the clockwise direction. In this example, pi1 completes the closed path in the clockwise direction, and the pi2 completes the closed path in the anti-clockwise direction. Corresponds example, pi2 completes the closed path in the anti-clockwise direction. That means, sir, in this particular example, how the pi1, pi2 are completing closed path in the same direction, opposite direction. Correspond to this particular example, here the pi1 and pi2 are completing closed path in the opposite direction. When the flux of the two inductors are completing closed path in the opposite direction, the sign of the mutual induced voltage opposite to sign of the self-induced voltage. The sign of the mutual induced voltage is opposite to sign of the self-induced voltage. Okay. On the other hand, suppose if you reverse the direction of current for this one, what is the direction of flux also reverses? Directional flux also reverses. How the pi 1 and pi 2 complete the closure path in the same direction. Even the pi 1 and pi 2 are completing closure path in the same direction, the sign of the mutual induced voltage is same as the sign of the self-induced voltage. The sign of the mutual induced voltage is same as the sign of the self-induced voltage. That means here every time to conclude this sign for mutual induced voltage, we should focus on the direction of fluxes. Direction of fluxes. But in the practical system, every time it is a little difficult to conclude the direction of fluxes. That's why to conclude a sign for mutual induced voltage easy way. To conclude sign for mutual induced voltage easy way, here one more simplified method is developed. There is a dot convention. With help of the dot convention, we can easily conclude the sign of the mutual induced voltage. The sign of the mutual induced voltage. First note on this one. First draw this figure, we'll conclude the note. Then after we'll explain dot convention. Somebody asked in the previous slide. Okay. Write the note. When the flux of the two inductors, write the note. When the flux of the two inductors, when the flux of the two inductors are completing closure path, when the flux of the two inductors are completing closure path, when the flux of the two inductors are completing closure path in the opposite direction, are completing closure path in the opposite direction, are completing closure path in the opposite direction, the sign of the mutual induced voltage, sign of the mutual induced voltage, sign of the mutual induced voltage, opposite to sign of mutual-induced voltage, opposite to sign of self-induced voltage. Sign of self-induced voltage. No, observe. Then to conclude the sign for mutual-induced voltage, here one more simplified method is developed here, dot convention. Dot convention. Let us see with help of the dot convention, how can you conclude the sign of the mutual-induced voltage? The corresponding first example here. Now every inductor is in the two ends, starting end and the finishing end. Every inductor is in the two ends, starting end and the finishing end. At any one end, this dotted point is indicated. Dotted point is indicated. For this one, I1 is entering a dotted point. What about I2 also entering into the dotted point? And corresponds example, I1 is living at dotted point. And I2 also living at the dotted point. If either both currents are entering, or both currents are living at the dotted points. If either both currents are entering or both currents are living at dotted points, at that instant, the sign of the mutual induced voltage, is same as the sign of the self-induced voltage. The sign of the mutual induced voltage is same as the sign of the self-induced voltage. Let us develop the equations. Now previously we discussed the two mutual inductances M12 and M21. Previously we discussed two mutual inductances M12 and the M21. Now while writing the equations, always assume as a M12, M21 both are exactly equal. That is equal to, we can give the common name for this one as a M. Now observe. Now correspond to first example. Let us write the respective equations here. Now correspond this example here. We can convert the V1 equal to. Corresponds example here. This V1 equal to, we can convert as a, whenever the I1 current circulating respect to self-induced EMF, we write this by L1 dI1 by dt. Now I1 is entering, I2 is entering. If both are entering, the sign of the mutual is a positive. In this one, the current of the second inductor produces mutual in the first one. The second inductor produces the mutual in the first one. current of the second inductor produces a mutual in the first one. Come to the V2. Now whenever this I2 current is circulating, self-induced EMF is reduced by the L2 dI2 by dt. L2 dI2 by dt. Again the current of the first inductor produces a mutual in the second one. Current of the first inductor produces a mutual in the second one. Current of the first inductor produces a mutual in the second one. Now these two equations are valid for the first figure as well as for the second figure. These two equations are valid for the first figure and as well as for the second figure. On other hand, the same equations you can write in the other way also. Do you remember in the basics of inductor, I conclude one point. E equal to, we can write this way, minus L dA by dt. And V equal to L dA by dt. Do you remember this one? In this example, there we supported as this negative sign. This negative sign can be supported with respect to Lenz law. Negative sign can be supported with respect to Lenz law. I hope all of you remember this one. The basics of inductor I concluded this one. Every time this V and this induced voltage both are indicated with the opposite sign. That opposite sign statement we can support with respect to Lenz law. Chaliye. Let us read the respective equations. In this example here, the same equations we can write this E1 equal to minus L1 dI1 by dt and M dI2 by dt. This E2 equal to minus L2 M dI1 by dt. In this example here, remember as this E1, E2 indicate the induced voltage. E1, E2 indicate the induced voltage. And this V1, V2 indicate the terminal voltage. V1, V2 indicate the terminal voltage. Okay. In the options, they may give like this or they may give like this. Both are the correct representation. Okay. Really. Come to the other two figures. Now correspond to these other two figures. Here. Here I1 is entering a dotted point and I2 is leaving a dotted point. But in this example here, I1 is leaving and I2 is entering. If one current is entering, other current leaving, the sign of the mutual is the opposite to sign of the self-induced voltage. Can you write the respective equations here? Whenever the I1 current is circulating, self-induced EMF, we write this for the L1 dI1 by dt. So for this one here, the current of the second inductor produces a mutual in the first one. What the sign is the minus dI2 by dt. Same analysis can repeat for V2 also. V2 equal to L2 dI2 by dt. Current of the first inductor produces a mutual in the second one. Now these two equations are valid for the third figure as well as for the fourth figure. First, can you note these figures, draw the figures and write the respective equations also. Traffic logic. For this one, put side reading dot convention. When the current is either entering or leaving, at both dotted terminals, at both dotted terminals. Sign of the mutual induced voltage. Sign of the mutual induced voltage. Sign of the mutual induced voltage is same as the sign of the mutual induced voltage is same as the sign of the self-induced voltage. When one current is entering and other current is leaving, when one current is entering and other current leaving at dotted terminals, sign of the mutual induced voltage, sign of the mutual induced voltage is opposite to sign of sign of the mutual induced voltage is opposite to sign of self-induced voltage. And one more point is generally correspond transformer every time what we do, we conclude as a this voltage ratio is directly proportional to turns ratio. We give a statement as a voltage ratio is directly proportional to turns ratio. And we give one more statement as a this current ratio is inversely proportional to turns ratio. This current ratio is inversely proportional to turns ratio. Generally every time for many problems we go like this. But for some of the questions what they do here in the data itself, they provide the dotted points also. In the question itself, they provide the respective dotted points and they give current directions. That's why whenever the dotted points and current directions are given at that instant, we have to write the relations very carefully. Because these relations are not valid for all the cases. Whenever any dotted points, current directions are given, according to that one only, we have to give the signs for this one. Where the ratio of this one equal to positive or negative, you have to conclude according to dotted points and current direction. If no information given, every time we assume as a voltage ratio is directly proportional to turns ratio with a positive sign by default. Here also by default with a positive sign, no information given. Magar, whenever the dotted point current directions are given, you have to do the calculations very carefully.